In the last several sections of Chapter 8, we're going to discuss periodic trends. So sections 8, 6 through 8.8 are going to be summarized in this video. Before we talk about certain periodic trends, let's review some terms. Core electrons and valence electrons. We, in the last video, did electron configurations, which show the arrangement of electrons in an atom. The core electrons are the electrons that are closest to the nucleus. They shield the valence electrons from the positive charge of the nucleus. So in the electron configuration, the core electrons are represented by the noble gas symbol in brackets. So they are the electrons that are closest to the nucleus. They are surrounding the nucleus, shielding the outermost valence electrons from the positive charge of that nucleus. Now, what's the deal with the valence electrons? The valence electrons are the outermost electrons. And when you have chemical bonds occur, it's these valence electrons that participate in that bonding. Now, not every single valence electron may participate in bonding, but when bonding occurs, it's the valence electrons that are involved in that. In the electron configurations, the valence electrons are represented by the sublevels that come after the noble gas symbol in brackets. Now, you may remember from prior chemistry, and if not, I'm going to review it now, that the periodic table with the designations of the A and B groups are pretty helpful. The representative elements, which are the A groups, the number before the letter A tells you how many valence electrons those elements have. So all of your elements in group 1A, your alkali metals, all have one valence electron. Even hydrogen, even though it's not a metal, it has one valence electron. It only has one electron, one valence electron. So one electron that participates in bonding. Group 2A, your alkaline earth metals, have two valence electrons. Okay? Now remember, the electron configurations for group 1A elements all end in an S1 sublevel. Group 2A elements end in an S2 sublevel, okay? And that sublevel is dependent upon which principal energy level it is, okay? Go over here to the representative elements on this side of the periodic table. Group 3A, 3 valence electrons. And those electron configurations end in an S2 P1 sublevel for the total of 3 valence electrons. 4 valence electrons in group 4A, 5 valence electrons in group 5A, 6 valence electrons in group 6A, okay, group 7A, 7 valence electrons, and then group 8A, 8 valence electrons for the noble gases, with the exception of helium, which only has 2 valence electrons, okay? So in the previous video, I talked about carbon's electron configuration, 1s2, 2s2, 2p2. And you say, well, carbon ends in 2p2, 2p1, 2p2. Where are you getting the 4 valence electrons from? Okay, well, from the S2 that fills prior to that. Okay, and the 2 core electrons would be represented by the helium symbol in brackets. Okay, so we're talking about periodic trends, but we need to keep in mind things like valence electrons and the fact that the core electrons sit between the nucleus and the outermost valence electrons. We also want to remember, okay, I just went over that these are the groups, okay? The vertical columns are the groups. But let's remember that as we go across, these are called the periods, okay, or the rows, all right? So we're going to talk about periodic trends. You can look in the textbook, and it talks about the history of the periodic table, which is very fascinating, very interesting. But originally, the periodic table was set up in order of increasing atomic mass. But it was seen that that was not the best way to have it arranged, because has been for many years in order of increasing atomic number. So we see that we have certain trends, certain patterns that repeat. And we're going to talk about 4 of them in this video and that are referenced in these sections here. We're going to talk about atomic size, okay? The diameter or the width of the atom, okay? Not its mass, but its size, its radius. We're going to talk about ionization energy. How much energy is needed to forcibly remove an electron from an atom? We're going to talk about electron affinity, the ability of an atom to attract electrons to itself. And we're going to talk about metallic character and reactivity. The first periodic trend we're going to talk about is atomic size, or the radius or diameter. As we go across the periodic table, the atomic size decreases due to the greater attraction between the positive nucleus and the negative electrons. So as we go across, okay, we have the larger atoms here and the smaller atoms here. Now remember, we're talking about atomic size, atomic radius, not atomic mass, okay? So we may have a greater atomic mass, but that is not the same as the greater atomic size. You have more electrons that are packing in to that principal energy level and causing a greater attraction between those electrons and the nucleus, so it's pulling them in closer. So it gets smaller as you go across. Over here, you don't have the same attraction between the outermost electrons and the nucleus. When you go here, okay, and you're going across in the same period or the same row, you're adding electrons to that same principal energy level. You're packing in more. So there's more of a greater attraction between those electrons and the nucleus, and they're squishing together tighter, okay? So the radius or the diameter decreases as we go across the periodic table. Now, as we go down the periodic table, we're adding additional principal energy levels. We're going from 1s to 2s to 3s to 4s. We are adding additional principal energy levels, which is widening that overall radius, diameter of the atom. So as we go down, okay, the periodic table, the increase in principal energy levels, okay, allows for the widening of the atom, and therefore a greater atomic size, radius, diameter, whichever term is being used to define the same concept, okay? So if you want to keep a little chart for yourself in your notes, okay, draw a little periodic table and leave plenty of space around it, because each trend we do, we'll summarize it with our little chart here. So atomic size decreases as we go across, and it increases as we go down. You have a chart in your textbook, figure 810, okay, which illustrates this trend with, showing you actual values. Let me just hold it up to the camera, okay, so you can see that, okay, showing the same thing that I have summarized in the corner of the whiteboard here. Let's do a comparison based on these trends. Let's look at the halogens, okay? Let's take 4 halogens. Let's take fluorine, bromine, chlorine, and iodine. And let's distinguish which one is larger, okay? Well, the trend is that atomic size increases as we go down. Okay, these elements are in the same group, okay? So we'll make the comparison very easily. So as we go down the periodic table, the atomic size, atomic radius increases. Well, which one of those 4 is at the bottom? Iodine, okay? So iodine would be the largest out of these 4. I should say which is largest. Let me correct my grammar there. Which is largest? Okay. Okay, because we're comparing more than 2. Okay. So iodine would be the largest, okay? Let's compare 4 elements in terms of which one is the smallest in terms of atomic radius, atomic size, diameter, okay? So we have within the same period, okay? we are comparing calcium. We are comparing vanadium, selenium, and what's the other? And copper. Okay. So those four we're comparing. Atomic size decreases as you go across the periodic table. So if we are looking which one of these is furthest to the right, the one that is furthest to the right would be ding, 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 ding. Trying to read backwards here. Selenium. Yes. Okay. So out of those four, selenium would be the smallest, okay? The second trend we're going to discuss is ionization energy, abbreviated IE. And there are some figures in your textbook, figures 8.14 and figure 8.15, which I'm going to reference in a moment. But what is ionization energy? Okay, atomic size is pretty easy to explain. But what is ionization energy? Ionization energy is the energy required to remove an electron from an atom. To remove an electron from an atom. Okay. Well, as we go across the periodic table, the ionization energy increases. Why? Think of what we have in a periodic table. We have on the left-hand side basically our metals. As we go to the right-hand side, we have the nonmetals. Well, metals readily lose electrons when they bond, when they form ionic compounds. Nonmetals want to gain electrons when they form ionic bonds. So you have the metals here, which readily give up the electrons. But the nonmetals want to gain electrons. They don't want to give them up. So metals on the left readily lose electrons, but nonmetals on the right do not want electrons removed. They want to gain them. So more energy is needed to forcibly remove an electron from an atom that does not want to lose it. So the ionization energy increases as you go across the periodic table, as you go from the metals to the nonmetals. The nonmetals want to gain, not lose. So if you want to take from something that tends to gain, a lot more energy is going to be needed to forcibly pull one of those valence electrons away and make it do what it naturally doesn't, is not inclined to do. Okay, so ionization energy increases as we go across. As we go down the periodic table, the ionization energy decreases due to the atom's larger size. So we had just talked about atomic size. We said as we go down the periodic table, the atoms get larger due to the increase in principal energy levels. So the atoms get larger, and that has the reverse effect on ionization energy. That atom gets larger, so those outermost valence electrons do not have the same attraction to the positive nucleus as if it was a smaller atom. So the ionization energy decreases as you go down because you don't have that same attraction or hold. So those outermost valence electrons can be removed with less energy than if it was a smaller atom which has a tighter grip or tighter hold, okay? So if we keep our little summary chart in our notes, okay, ionization energy increases as we go across the periodic table, and ionization energy decreases as we go down. Okay, we can keep that with our little summarized periodic table. Okay, let's do some comparison. Okay, let's look at four elements that are either in the same period or the same group. Okay, the same row or the same column, and let's compare. Which of these four would have the lowest ionization energy? Okay, so we look at the periodic table, we locate the elements that we are comparing. So we're comparing magnesium, we are comparing sulfur, we're comparing chlorine, and we're comparing aluminum. Okay, ionization energy increases as we go across. So the higher ionization energies would be on this side versus this side. So we want to know what's the lowest. So lowest meaning that it decreases. So we want to look for an element that is more so on the left side of the periodic table, namely a metal. Okay, because metals have the lower ionization energy. So we look at the periodic table. Magnesium would be the element with the lowest ionization energy. Magnesium readily will lose its 2 valence electrons in forming an ionic bond. Okay. Aluminum will lose 3 valence electrons in bonding. The sulfur and chlorine want to gain. They're nonmetals. So the lowest ionization energy would belong to magnesium. Okay. Now let's compare 4 alkaline earth metals in group 2A, which has the highest ionization energy. So the highest ionization energy would be an increase, okay? So we have the terms lowest, highest, referring to the trends of increasing or decreasing. So don't let those words confuse you, okay? If something is lower, it's decreasing. If it's higher, it's increasing. So which has the highest ionization energy if we're comparing 4 alkaline earth metals? We are comparing magnesium, we're comparing calcium, we are comparing beryllium and barium. Okay, so the trend is that as you go down the periodic table, it would decrease. So the reverse would be the increased one would be further at the top. So that would be for beryllium. Okay, so the highest ionization energy, beryllium, is up here at the top. Okay. Ionization energy decreases as you go down. The atomic size increases, so the ionization energy decreases. You have less of a grip. So, but that small beryllium has a higher ionization energy. So I referenced 2 charts in the textbook. So I'm going to first go reference chart 815, okay, because that is actually a little bit more similar to what I have on the board over here. So you see that ionization energy, as you go down, it decreases, and as you go across, it increases. And this table here actually lists ionization energy values in kilojoules per mole. So it actually gives you energy values there. Okay, so example for what we just compared here, they actually have these elements listed there. Beryllium is at 899 kilojoules per mole. Magnesium, 738 kilojoules per mole. Calcium, 590 kilojoules per mole. And barium, 503 kilojoules per mole. So beryllium has the highest. Okay, and that chart, figure 815, gives you the actual values. Chart 814 talks about ionization energies as well, but it doesn't give you, it's presented a little bit differently. It's presented as a line graph, more in contrast to the other one, which is a blocked graph. Okay. Figure 816 talks about ionization energies, second and third ionization energies. The first, to remove 1 electron from an atom is less energy needed than if you want to rip away a second or a third one. So figure 816 it shows values for second and third ionization energies. And if you're comparing sodium, okay, sodium forms a +1 ion. It loses its 1 valence electron with relatively low energy, okay, 496 kilojoules per mole. But what if you wanted to rip off a second electron from sodium? It doesn't want to give the second one away. It just wants to give the one away. You would need almost a 10-fold increase in energy, okay? 4,560 kilojoules per mole of energy needed to rip that second one out. And then if you wanted to rip a third electron off of sodium, now remember, sodium only wants to give one away. You would need 6,910 kilojoules per mole of energy to rip a third one away. So you see, as you take off subsequent electrons, more energy is needed. Okay? So figure 8.16 talks about second and third ionization energies for comparison's sake. The third trend that we're going to discuss is electron affinity, abbreviated EA. Sometimes electron affinity is also referred to as electronegativity. The terms are very similar. The definitions are similar as well. The ability of an atom to attract electrons to itself, okay? Electrons are negative particles, so therefore the term electronegativity is used to refer to the same thing. So affinity is a likeness and attraction, so the ability of an atom to attract electrons to itself. So the trend for electron affinity is the same exact trend as ionization energy. It follows the same trend. As we go across the periodic table, electron affinity increases. Remember, the metals on the left want to lose electrons, but the nonmetals on the right want to gain electrons. Electrons are attracted to the nonmetals, okay? So the nonmetals on the right have a tendency to gain electrons, have an affinity towards electrons because the nonmetals attract electrons, okay? As we go down the periodic table, electron affinity decreases, again, due to the atom's larger size, okay? A lot of these trends are interrelated. The atom's size increases. You do not have that same attraction between those outermost electrons and the nucleus. So those electrons that are on the valence shell, the outermost sublevel, okay, they don't have that same you don't have that same affinity. They're not that same attraction because the atom is larger and it's not pulling close to it electrons, okay? It can't keep a grip on them because it's getting larger, so it's not attracting, it's kind of just letting them go, okay? So the trend is exactly the same. The definitions are different for ionization energy and for electron affinity, but the trend follows the same. So let's compare the same four elements, but let's switch it up a little bit, okay? Out of these four, which has the highest electron affinity? Okay, so if we're comparing magnesium, we're comparing sulfur, we're comparing chlorine, and we're comparing aluminum, electron affinity increases as we go across. So as we go across, the atom that has the higher electron affinity would be somewhere where we have a nonmetal, because the nonmetals tend to attract electrons to themselves. And the one that's furthest over is chlorine. So chlorine has the highest electron affinity. Okay. What if we're comparing the alkaline earth metals? Magnesium, calcium, beryllium, barium. And we are asked which has the lowest electron affinity. So the lowest electron affinity would belong to the largest of those atoms, okay? And the largest of those would be barium. Barium would have the lowest electron affinity. Electron affinity decreases as we go down, okay? Figure 8, what's this, figure 8.16 gives you electron affinities figure 8.16. Okay. The last periodic trend that we're going to discuss in Chapter 8 is metallic character and reactivity of metals. And there are figures, figure 8.17 and figure 8.18, which are used to help illustrate this concept. But this concept's pretty basic at this point. Metallic character and the reactivity of the metals decreases as we go across the periodic table. Now we know at this point, between prior chemistry and this course, here are the metals and here are the nonmetals. So yes, metallic character and reactivity decreases as you go across because your elements go from being metals to nonmetals. Remember this chart? Okay, I think I showed it at one point. Okay, so you see most of the elements that we have on the periodic table are metals. But then when you go across over to the right-hand side, okay, you see that you have the nonmetals. Okay. So metallic character decreases as we go across. You have things such as the copper wire, metal. Okay. Aluminum, which are both metals. And then all the way over on the far right, sulfur, non-metal, okay? Metallic character and reactivity increase as you go down the periodic table. Because as the ionization energy increases, the electrons are more likely to be lost by the metal cations and gained by the non-metal anions. So therefore, they become more reactive due to that increase in the ionization energy. Okay. So let's do some comparisons for the least metallic and the most metallic. Okay. I'm sorry, this should say ionization energy decreases. Sorry. Okay. All right. Metallic character and reactivity increase because the ionization energy decreases as you go down. Therefore, not having that same grip, the electrons can be lost by the metal cations and then picked up or gained by the non-metal anions, therefore increasing the reactivity of that metal because the outermost electrons are moving around. Okay, just wanted to clarify that. All right, so let's compare four elements. Let's compare four elements and see which one is the least metallic, okay? Sulfur, sodium, argon, aluminum. Well, right away you should know two of them aren't even metals. So the one that is the least metallic would be the noble gas argon, because it's not a metal. It's a noble gas. Okay, so as we go across the periodic table, metallic character decreases. Let's compare these four elements and distinguish which one is the most metallic. Now these four elements are all alkali metals in group 1A of the periodic table. We have lithium, sodium, rubidium, and cesium. Metallic character increases as you go down the periodic table, so the element out of these four which would be the most metallic would be cesium. The alkali metals are very reactive, especially with water. I have a video that I'm going to link to this video that shows you demonstrations, which I cannot replicate in my house, of how you could react the alkali metals with water and see what happens. So that video is going to follow this.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. Oh, thank you very much. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John. Go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion.
And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason they wouldn't let us have any of that. Still, there you go. Today's lesson.
Never mixed alkali metals with water.